Welcome everyone. Thank you for being here. Today we'll be talking about combining CNNs and conventional algorithms to create a low compute vision solution. So I want to start with a question. That question is, are CNNs always the best choice for every computer vision problem? And by all of the absolutes that I put into that sentence, you can probably guess that I think the answer is no. So I've got an idea here that I want to present, and that is that sometimes simpler algorithms are actually the better choice. And there's two other parts to this. One is that algorithms, these simple algorithms, can be guided by CNNs in order to overcome some of their limitations. And also that it's really important to simplify the problem first and to leverage constraints in order to be able to utilize simpler algorithms. So I'm going to try to make a case for this by telling you a little story about creating the smart garage. Now, really, this is only chapter 1 of the story. The rest is still being written. So who is the author of this story? Well, I'm part of the Chamberlain Group. We are a global leader in access solutions and products. Back in the pre-COVID days, while you guys were all probably commuting to work, I'm sure many of you used one of our products every day when you would leave your garage or come home. You probably had a LiftMaster or Chamberlain garage door opener that would give you access to your house. You probably still have that garage door opener. You're probably just not using it nearly as much anymore. But we are more than just garage door openers. We have commercial products. We have automotive products. We have a variety of other areas that we are in. But more importantly, we want to not just be about opening and closing garage doors, but we want to be about giving our customers the power of access and knowledge. And it's that second part, the knowledge, that I want to talk a little bit more about today. So creating the smart garage. Well, recently we launched a new product, a new flagship product, which is a garage door opener that has a camera built into it. And we've been thinking, how can we make this product smarter? There's a couple pieces of knowledge that we think that we are well suited and uniquely positioned to provide to our customers. And those are knowing when a vehicle leaves, when a vehicle arrives in the garage, and then related to that, knowing if a specific vehicle is currently located in the garage. To provide this knowledge, we realized that we needed to solve the problems of vehicle presence and vehicle re-identification. Obviously, one of the first places that we started to look was to CNNs. And in looking there, we came across quite a number of strengths and weaknesses of CNNs. Beginning with the strengths, CNNs generalize really well to unseen circumstances. You train it on one set of data, and you validate it on different data that it's never seen before. So this works really well for a wide variety of customers who have garages that we've never seen before. Also, CNNs can be trained for a variety of tasks. You can use it for scene classification, for object detection and localization, semantic segmentation, pose estimation, and plenty more. Plus, in a lot of these problems, CNNs give state-of-the-art results. They give higher accuracy than the majority of other algorithms, especially in generalized scenarios. But CNNs also have their weaknesses. In order to get all this generalization, you really need a large training data set. Also, CNNs are known for having high compute requirements and using a lot of memory. Granted, they're better than some other neural networks, but they still have pretty high memory requirements to store the weights. Well, even with these weaknesses, we certainly looked into CNNs, and we did a bunch of research, and we do use them in our final results. But here's some of the stuff we found. So using something like YOLO or SSD for object detection, well, we ran into some accuracy issues, actually. Even though CNNs are state-of-the-art, they're not trained for our particular use case. You can see in this image that the scene taken from the garage camera, it only sees the back end of the cars when they're parked. And this is not what most of the training data looks like in the data sets that are used to train these neural networks. So if you just take an off-the-shelf neural network with pre-trained weights, we didn't get very good accuracy. we decided to add another layer in there using video and object tracking. So we could actually see the vehicle entering. While the vehicle is more visible and we see more than just the back end of the vehicle, the neural networks get a higher hit rate. We're able to track that box as it moves, as it crosses the line, and able to see that the vehicle has entered the garage or the vehicle has left. And that gives us a really good indication of whether there is a vehicle currently present in the garage or not. But this comes at a cost. There's a pretty high cost to analyze all that video, especially if you don't know a vehicle is entering or exiting. You have to analyze quite a bit of vehicle in order to catch that vehicle coming and going. The second problem that we wanted to solve was vehicle re-identification. And we looked at 3 CNN-specific solutions for this problem as well. We started with make and model classification. This one, as with the others, ran into some accuracy issues, especially for our data set. So you see that blue Subaru Forester over there in the right side of the garage? Well, oftentimes that would come back as a Toyota RAV4 or a Honda CR-V or one of the other compact SUVs out there on the market. Getting an exact match on the vehicle that we are looking for proved to be quite difficult. Plus, a lot of the off-the-shelf algorithms that we attempted to use didn't even get a very good hit rate on finding the vehicles located in these positions. A second thing we looked at was license plate recognition. This one seems like a pretty obvious choice if you want to re-identify a vehicle. Take a look at its license plate. If you get a match, same vehicle. But as you can see, once again, the position of the camera causes us a bit of a problem. We can't see the license plates when vehicles are parked. They're just not visible. If we want to catch that license plate as the vehicle enters or as the vehicle exits, we run into the same problem as before, having to track video, having to look at quite a few more frames in order to find the frame where the license plate is visible. On top of that, if we want to process this in the cloud, we're dealing with H.264 compression, and even before it's compressed, we have great dynamic range between the outside and the inside of the garage. So oftentimes the license plate is either blown out or it's in a deep shadow. And if there's not very good lighting, we get lots of motion blur. All of this means that a license plate is not visible in many frames. In the frames where it is visible, it's very difficult to read. And in some states, cars don't even have a license plate on the front of the vehicle. It's not required. And so this particular solution, if we relied too heavily on license plate recognition, just flat out would not work in certain states where license plates are not required on the front of the vehicle. Unless, of course, the user backs into the garage. But still, it's not a broad scenario that we can apply this to. Probably the most promising is something called pairwise similarity. So this is with neural networks that are trained with something like a hard triplet loss or a cross entropy loss. They're trained to produce an output vector that can be compared to other output vectors using some type of distance metric. And if you put in 2 images, different images of the same vehicle, the distance metric will return a short distance. And if you enter 2 images of 2 different vehicles, the distance metric should show a greater distance. This is what's used for things like facial recognition and a lot of other re-identification problems. This is looking pretty promising for vehicle re-identification as well. There's a lot of work to do, especially in terms of image alignment, things like that. But the biggest problem, again, is the data sets. Right now, there aren't any free data sets out there. All the data sets require academic use only in their restrictions. And also a lot of those data sets, even if we were to license them for commercial use, they don't have data that is very representative of the data that we want to look at. And so we are not sure how well the results are going to pan out for us. And we have another problem beyond just the limitations of the neural networks. We have a cost constraint. So when this product was developed, vision wasn't really part of the equation. And so what's left for us trying to solve the vision problem to work with is we have a single core of the ARM processor that's available to us. We have a small amount of memory left over for us to use. And if we wanted to run this in the cloud, we would have to keep the cloud expenses minimal as well, because we want this feature available to the majority of our customers so that most people can benefit from this. So we don't want to have to charge a really high monthly fee for it. So what can we do? Well, we decided we would try to look at simplifying the problem. Took a couple approaches to simplifying the problem. The first one I want to go over, I call simplify the question. So all these neural networks, they produce really rich metadata. They produce a complicated answer. And that answer then needs to be interpreted. The answer needs to be simplified. We thought, well, what if we try to get the algorithm to produce the yes-no answer instead of having the algorithm produce really rich metadata and then we further simplify it? So can we ask the question differently? Can we simplify earlier in the process so that we're asking a simpler question, that way we can use a simpler algorithm instead of simplifying the answer? Our answer that we're trying to get is just a yes or no, just true-false answers. So I'll get into a little bit more on how that works. But the next process that we looked at for simplifying the problem is to look for useful constraints. We were stuck with a lot of bad constraints, not being able to see the license plates, for example, low CPU, low memory. But we looked for some useful constraints, such as the camera's fixed location. We don't really need as much generalization because the camera is stuck in one spot. There's a limited number of vehicles. None of us have Jay Leno's garage, and so we don't really have to look for any type of car. We have to look for the specific cars that are owned by this user. The vehicles also generally park in a fixed location. There's not a lot of wiggle room in most people's garages, which means we know where that region of interest is going to be. At least once we've seen it once, we know where it's going to be in the future. Personal habits. People usually park on the same side of the garage over and over again with not a whole lot of crossover. That's not true of everybody, but it's true of enough that we can leverage that. And then something I call temporal consistency in the background, which basically means people don't clean their garages, so the clutter is there over and over and over again. So if we have an algorithm that latches in on that clutter, we can make use of that. And all of this means that we don't really need a neural network that's super generalized. We can solve this problem with something more specific. So we put together a little hybrid solution. I call it hybrid because we use some neural networks and heavyweight stuff, and we also use a simple algorithm. And I'll show how those work together a little bit later, but I'll start with talking about the simple algorithm that we chose. We selected, for now at least, a modified histogram of oriented gradients. Very common algorithm in computer vision. We like it because it lowers the spatial resolution. This has a couple benefits. One, after the hog is generated, any remaining parts of the processing pipeline have less processing work to do, but also it gives us some flexibility. If that car moves a little bit from one side to the other, the output vector is very similar. Also, because it produces a grid output, we can translate that further for additional translation invariance. And this grid nature also gives us the ability to pretty easily create a nice attention mask to know which features are important, which features are not important. It's also pretty commonplace to understand how to compare two hog vectors with each other to find the similarities. So you can see on the screen an example of some of our features that have been, we've built this attention mask on them to know which vectors are the important ones to determine if a particular vehicle is located in the spot or if that spot is empty. So anyways, I will get to that bottom point of creating the training mode to automatically gather images for known conditions. But first of all, I want to show you a nice complicated diagram of what that fast scene matcher looks like. Put that on there, not necessarily for you to read. I know the font is way too small, but it's just to show that, yeah, we did put a lot of thought into this. But the summary is on the left. It's pretty straightforward. We gather images with known conditions. Again, I'll get to how that's done in a second. We extract those features, we build the attention masks, and we process all of that into a library that we keep. So this is a library of what the scene looks like for specific known conditions. Then during run mode, we gather the scene, gather an image of an unknown condition. We're going to extract the same set of features. We compare it to our library, taking into account those attention masks, and we find the best match. Which one of the known conditions is this a closest match to? Or maybe it's not a match. Maybe it doesn't match any of them within the associated threshold. That's the basic of how our fast scene matcher works. Again, we're leveraging that fixed camera. That's the biggest thing that we needed to have in order for this to work. To really make this work well for the user, though, we put that fast algorithm into a larger meta algorithm. And this meta algorithm actually starts off with training mode, with what we call training mode. So in this, we're actually running multiple CNNs. We have a PoseNet to find out the location of the garage door relative to the camera, to make sure the camera is positioned right, to make sure we know exactly where the regions of interest are for the parking spots. We use YOLO to detect the vehicles as they come and go. We have some object tracking as those boxes move around. We've got regions of interest. We've got line crossing. We will be adding license plate recognition eventually. All of this allows us to hopefully understand to some degree of accuracy when vehicles are located in the garage and outside the garage, which allows us to capture some of these known conditions. But then, as I mentioned before, the accuracy, at least for us, with how these neural networks are trained so far, the accuracy is not quite where we want it to be for the final product. So we have one more step in place where we leverage user input. We ask the user to fix our mistakes. The algorithm is good enough that we find the users are not too concerned about fixing a few mistakes that the algorithm has made. So that's a workable solution for us at the moment. The output of this is this set of known condition images. We process that, put that in the library, and then we kick it over to our hummingbird algorithm. The train mode you could think of as the king of the jungle, big, heavyweight, does a lot of stuff. We've got the hummingbird now in run mode. This guy runs fast, but he doesn't do a whole lot. So this output, given a scene for each parking spot, is going to tell us, is it one of our known conditions of what vehicle A, vehicle B, empty? Or is it indeterminate? Does it not match any of those? In which case, you can see run mode can kick over to retrain mode with this ask for help. That's when run mode doesn't know what's going on in the situation. We can run that heavyweight algorithm a couple more times and see if we can make sense of this interesting condition. This is something internally that we're referring to as a guide follower design pattern. The input can come in and it can go for train mode up to the guide. This is our big, heavyweight, expensive set of algorithms. It's kind of slow, but it's very generalized. It can understand quite a few different scenarios, but we only run it infrequently when it's really necessary. That produces output that informs the follower algorithm. The follower algorithm is very specialized. It only works if it has that information, but it's fast, so it can be run frequently, and it's very inexpensive. It also, as I mentioned before, it has to know when it doesn't know. So it can ask for help and then ask the guide algorithm to give it a little bit more information to make sense of this unknown situation. So what are the results? Well, I'm going to focus a little bit on single frame just because I wanted to be able to compare apples to apples and just show you a little bit. And also single frame mode is kind of where that cost is saved when running this in kind of what would be termed like an inference kind of mode. The train mode doesn't run quite as frequently, and so that's not our focus. Our focus is on run mode. So we actually tried a few versions of YOLO, and you can see those there. The bottom line there is that we really couldn't get the accuracy we wanted in detecting vehicles. A lot of that is due to the training data. We really need to gather a stronger training data set that is representative of our scenario in order to be able to get the accuracy we want out of YOLO. Also, as you can see down near the bottom, the cost. The cost is pretty high. Running these types of algorithms in the cloud is not a cheap thing to do. On the flip side, you can take a look at the results of the fast scene matcher. So these two columns, the first column, we use 4 example images for the vehicle in the position, 4 examples of the vehicle of the parking spot empty. And in the second one, we added a few more, up to 7 of the vehicle in the space and still 4 showing the space empty. And you can see our algorithm is performing quite well for detecting that a vehicle is present, detecting that a vehicle is absent, and also detecting that a specific already seen vehicle has returned to the parking spot. It's also doing a pretty good job now. We have some improvements we need to do, but we're doing a pretty good job at recognizing the unknown condition. And that allows it to kick back over to train mode and to gather some more samples so that it can understand this condition as well. That's the yellow rows. One of the biggest things for us, though, is that cost savings. It really brings it in order of magnitude down from the neural networks. And the really big one for us is the ability to run this on our existing hardware. So we expect once we finish our optimizations that we'll get 2 frames per second or probably more, maybe up to 5, running the follower algorithm on the existing hardware. And remember, this hardware was deployed out to the edge without the idea of vision in mind. This is a retrofit. So our goal really is to have this train in the cloud inference on the edge happening. Obviously, our training is not the conventional training. This is our guide algorithm running, and inference is that follower algorithm running. So a few takeaways. First thing I want to say is it's important to simplify the problem first. If you want to use a simple algorithm, you need a simple problem. Identify the core goal. Try to simplify the question that you're asking instead of getting a complicated metadata and then simplifying the answer. And then very important is to identify and leverage any constraints on the system that are useful to you. I think with this, I've made the case that at least some of the time using a simpler algorithm can actually be the better choice. Obviously, you have to simplify the problem first. That way you can get away from needing to use a more generalized algorithm like a CNN. And then also, if you bring CNNs back into the picture, at least some of the time, there are ways to overcome some of the limitations of the simple algorithms. And more importantly, to add some automation to bring back and preserve some of the magic that we've come to expect from deep learning, but to do that at a much lower cost. Thank you.